See the section. It is a section, you can take it as I. For the elastic strain, stress, elastoplastic element, we taken as elastoplastic element. If it is an exactly plastic analysis, that's it. That's it. So if it is increasing the strain, the stress is same that fiber. The next part, later fiber reaches the elastic stress. So previously it is the compressive stress, it is a tensile stress. M is equal to sigma y into Z. Z, section modulus. Okay, section modulus. So now it is the section compressive force, tension force. What is the M? Moment carrying capacity, MP. Sigma y, say ZP, section modulus. We can call it as a section modulus for plastic modulus. You can call it as a plastic modulus also. Plastic modulus also. Okay, so what is that value? We'll see it. How you'll get this value? So find out the compressive force or tension force. This is the compressive force, this is the tensile force. This distance, lever arm. You can get C or T multiply with lever arm. You can get the moment. In this moment you can separate sigma y, you can get the section modulus. For plastic analysis, that is a plastic modulus. Okay, if you see that, now you can see it. If you see, one thing you can observe, if it is like this, irregular shape, not a symmetrical, sir. Symmetrical with respect to y-axis is symmetrical, with respect to x-axis is unsymmetrical. If you take in centroidal axis is CG, you find out the CG here. For elastic analysis is same. It is Fy. It reaches maximum stress. Fy. So, sir, it is maybe. If you see, if you say me, if you taken this is a, sorry for your understanding, better understanding. So see, the area is highest in top, so maybe CG is not an area. Moment. CG, how can you find out the CG? Center of gravity. Moment. If you see, it will come like this. Maybe CG is here. So to take in consider, it is maybe reaching Fy before this, because this length is very high, small na? Fiber. It is reaching most. Strain is higher at this location. Strain is higher this location compared to this location. So strain is higher before reaching it is reaching Fy before this point, top fiber. It is the top, it is bottom, you can consider it. Okay, so this is maybe less than Fy, less than Fy. So if you consider this is a compressive force, it's a tensile force, compulsory C or T as a compulsory equal. Sir, how can it equal, sir? But C, what is C is what is C? What is C? This stress value, the stress value may be F. It's not reaching F. Why? Stress multiply with area. Half is there. Multiply with area. If you consider this area is higher than this area, A1, A top, A bottom. This A top. Tensile force, if you consider is it's reaching Fy, but area is less. But this area is less and Fy is higher. In this area is higher, Fy is less. So if you consider both are compulsory equal, otherwise the equilibrium is not attained. every force must, if it is a stationary is there, all forces should be balanced. If it is not balanced, the body is moving. It is moving, it is a kinematics, not a static. Okay, so CRT is like equal. So don't feel that, sir, so this is, it's not reaching Fi, how can you get it? So both are equal. C and T are everywhere equal. But if you see moment, plastic analysis, if you see the plastic analysis, this plastic analysis, first it reaches the max, see, first it reaches the maximum here. You already know it. It reaches maximum Fy. Later, the next part also reaches Fy. Next part also reaches maximum. At that time, it reaches also Fy. Next part is reaching Fy. Next part is reaching Fy. So like this, it will come Fy, Fy, every fiber reaching the Fy. So it will come like this. It will go. Neutral axis is changing. Neutral axis is shifting. Sir, how why it is shifting, sir? Because, so same, this is the compressive force, this is the tensile force. C or C, T should be equal. C and T should be equal. If you see, this is Fy, this is also Fy. Both are Fy, na? So what is C? Fy, Fy. There is no of Fy, everything is Fy. And area? Area in that region. Okay, area in that region. Top. So tensile force, tensile force, tensile force also same Fy. Area should be in bottom. Area should be bottom. Both are Fy. Both are Fy. So compulsory C should be equal to T. Area top should be equal to area bottom. Area top should be equal to area bottom. So for both area should be equal. That's why the neutral axis may be not an CG axis. This is a center of gravity, not a area, equal area axis. This is equal area axis. This is equal area axis. That means the top area, this total, this top area and bottom area should be equal. Are understood? This is area, this is area under compression. So that's why the neutral axis is shifting in a plastic analysis. Should be equal, the area under compression, the area under tensile should be equal. But if you take an elastic analysis, no need to make it areas are equal because the stresses are different. Some portion is reaching Fy, some portion is not reaching Fy. So the axis is CG axis, center of gravity axis. This is the equal area axis. You can call it as a equal area axis. Are understood? Equal area axis or plastic neutral axis. Plastic neutral axis. This is center of gravity axis, CG axis, or elastic neutral axis. Elastic neutral axis. Okay, we will find out how it is. We will we will do the problems. So that's the first one you have to understand. Neutral axis is changing. It is not a constant. It is not the same as CG axis. Okay, you already know these things in a bending stress analysis and how the compressive force, tensile force, or stress is not reaching. These are all discussed in reinforced concrete. Concrete, RCC, they will exclusively discuss compressive force, tensile force, lever arm. You get more information at that unit. No need to discuss these things. Okay. So today we will discuss another points. So those points are load factor and the factor of safety and the shape factor. Shape factor. Shape factor. Okay, are understood? So first we will discuss what is shape factor. Shape factor is if you same for the same section moment carrying capacity in the elastic analysis. Elastic analysis is sigma y into z. You already know it. How to find out z? Z is like I by y. Otherwise you can find out by the compressive force, tensile force, you can easily find out. Otherwise, sir, if it is like this irregular shape, y is changing, na? Y top is changing, y bottom is changing. You understand? This is a y top, this is y bottom. Which one is taken, sir? Which one is taken? Z is I by y maximum. Which one is maximum? That is taken as a Z. For the same section, moment carrying capacity, ultimate moment carrying capacity, or plastic moment is same sigma y into ZP. This ZP is different, na? So you can easily find out by this area. This is, na? This is, you can find out C and T, multiply with distance, you can easily find out what is Z. You will find out it. Okay. So that is the section modulus for plastic analysis. Plastic section modulus. ZP is a plastic section modulus. So if you take in this ZP by Z is called shape factor. Sir, why it is useful? By this you can say how much strength is stored beyond elastic point. Understood? If something one section is there, something I section is there. I section is there. So ZP by Z is something 1.2. That means what? That means if it is M is 50, ZP is 60. ZP is 60. So that means what? It's a 1.2. 20% is all 20% compared with the elastic analysis is already stored in the system. You can say it, na? You can say it by the shape factor. You can say how much energy is stored beyond the yield point. You can say it, na? You can say it. That is the purpose of the shape factor. So okay. So if it's M is general elastic analysis strength is 50. So plastic analysis you can say is 60. You can say at least, so what by 6? 6 8 6 8 0.8 percentage. 0.8. So not 0.8, 60 by 50. So 5 5 10 12 12 1.2, exactly 1.2. So 20% of strength is stored beyond the elastic point. You can say it, na? You can say it like this. So that is the use of the shape factor. Sir, next, what is the factor of safety? Factor of safety. Factor of safety. If you say it's the factor of safety, so factor of safety, the maximum stress, taken a yield stress, only yield analysis, elastic analysis, we consider if we reach in the last fiber is yield stress, we call it as a failure. That's it. If any fiber, last fiber reaches to F5, yield stress, it is failure. So if you design the section, for that moment or anything, we will design up to F5. If it is reaching F5, it is failure. But in reality, we won't design like this. We won't design like this, sir. If it is say stress, it is Fy. If it is reaching Fy, that is the strength, capacity. We call it as elastic analysis. Na? That is a failure. We will design like, you think that you will design like that, the last fiber is reaching to Fy. But in reality, we won't decide. Because, so we won't stretch the system up to the edge. We will give some relaxation. That means, if you applied a 50 moment, it reaches to Fy like this. Okay, you can just take it. We will design the system. Only for if it is 40. So you can't understand. Okay, I will say it again. We won't design the system reaching to Fy. We will design the system like it won't reach Fy. It's below Fy. Because we won't stretch the system up to edge. Understood? We will design the system like It reaches to only some part. If Fi is 250, something it's taken 250. Exactly, we won't design. We won't design. We will design only the system reaching to 200 or 150 or 160 only. We will maintain some factor of safety. Are understood? We will maintain some factor of safety only. Okay. So because unexpected loads will come, unexpected loads. So if a small unexpected load will come, it will collapse. How it is? It's a very bad, no? So we will design the system like it reaches to only certain value of Fi, certain value of only Fi, only 60%, 70% of Fi only. We won't design up to Fi because it is the capacity of the section. We won't design used to total full elastic capacity, not a plastic capacity. So Fi is divided by allowable stress. Allowable, we will allowable certain part only. That is called factor of safety. Okay, that is called factor of safety. So what is our load factor? Load factor is plastic moment capacity, plastic moment capacity or plastic moment divided by allowable moment, not a elastic moment or elastic capacity, only allowable moment of resistance, or you can call it as a resistance capacitor. If you see, the shape factor is section modulus, plastic section modulus divided by elastic section modulus, elastic. Okay, but if you take the load factor is plastic moment capacity divided by only allowable, not elastic also, it's allowable moment of resistance. Allowable means this is allowable stress, na? This is allowable stress, so we can call it as Fa. We taken as Fa. If you see, what is the plastic moment capacity? What is the plastic moment? Plastic moment is Fy into Zp. Allowable is Fa. Fa into Z section modulus only. We will only allow Fa, not Fy, because we maintain factor of safety. If you taken, this is what a factor of safety. This is what a shape factor. That is called load factor. Okay, that is the idea. So load factor. See, one thing you can observe it. It has a certain capacity in a yield modulus. Yield analysis, it has a certain capacity. Beyond this also it has a capacity, that is a plastic analysis. But we won't, in general, we will feel that we will design for the elastic analysis for up to yield stress. But in reality, we won't design that member for the yield stress. We will design that member for only allowable, certain level only. We will maintain some factor of safety. So now you can see, that is the line for elastic analysis or yield stress. This is line for next beyond, it has a plastic. In general, we think we design for this section, for this stress. In general, we will design for very less stress. You will learn design, stress, what is allowable. Those are things in RCC. Okay, RCC. This is exactly idea. Okay, I got the idea. This is allowable. This is the yield stress. This is the plastic analysis, plastic moment capacity. Beyond. Okay, are you line? Follow. So now we will find out various sections. Previously I said it is 1.2. Na? For different sections, what is the shape factors? What is the section modulus? We will design it. We will find out. Can you find out? So now you will find out. Just very small problems. I will do it for your purpose. Okay. So if it is a I section, symmetrical I section, the size is 100, so 12.5. So height is 150 mm. Height is 140 mm. Take Fy is 250 Newton per mm square. Determine the shape factor. Shape factor. Shape factor. So if you think it is exactly symmetrical axis, symmetrical section, the plastic neutral axis and the elastic neutral axis both are same. Exactly off. It's exactly off now. Exactly off. It is a 75. Exactly off. CG also and equal area axis also same. So if it is unsymmetrical, both are changed. How it is changed, I will show you later. Okay. So find out the shape factor. Find out the shape factor and also plastic moment. Plastic moment capacity. Plastic moment resistance. You can call it as a resistance. That's it now. So that's it. You can find out. So can you find out? So you can easily find out. See, M is, if you want elastic, if someone is asked what is the moment carrying capacity by elastic analysis, M is sigma y into Z. What is Z? Z is, you can find out I, moment of resistance, moment of inertia, divided by y, 75. You can easily find out. Otherwise, you can find out the strain diagram is same thing. You can find out the strain diagram. You can find out this is the stress reaching. This is the stress reaching. Okay. So every section is something different. Now. So this is stress. You don't remember. This is a strain also. Strain diagram. Stress, and you can find out the area. You can find out the area, and you can find out the C, and you find out the section exactly where the compressive force exits. CG of this off portion. CG of off portion. It is too difficult. Too deep. Not difficult. You can find out, but no need at all. No need at all. So if you find out the I by Y, that will same. That will same. Otherwise, you can find like this also. That is hectic. No need at all. So that is exactly I by Y. You can find out moment carrying capacity by elastic analysis. But MP is sigma Y into ZP, plastic section modulus. Sir, how can you find out the plastic section modulus? I said plastic section analysis is find out. I will find out. I will find out. Okay. So exactly equal area axis. You have to find out first neutral axis for plastic analysis. That is an equal area axis. So exactly if it is exactly equal area axis, that's it. Equal area axis only. So now you can find every stress is reaching to the same portion. Same stress. Same stress. Na? It is Fy. It is also Fy. Same stress. Now you can easily find out the compressive force and tensile force. 1 minute. Hello. చెప్పు సరే నేను చూసుకుంటా లేదు ఒకటి బండి అవసరం లేదనుకుంటా నువ్వు వెళ్ళిపో నేను చూసుకుంటా see so what is M is compressive force tensile force multiplied with lever arm. Are understood? So this is exactly this is exactly that. Okay. So the thickness is also 12.5 mm. 12.5 mm. Okay, 12.5 mm. So now you can see. Can you find it? Can you find it? So compressive force. What is the compressive force? What is the compressive force? Total compressive force. Every fiber reaches to Fy. Fy is, you already know, it's a, what is that value? It's a 250. Fy is a 250. Fy is 250. No need at all. Fy is 250. No need at all. So we want to find out Zp only. So remaining area is what? Area is what? See, area 100. What is this area? What is this area? That area is what? This area is, you can call it as A1. It is 100 into 12.5. This area is what? Remaining area. So I will indicate here. This is area is 100 into 12.5. This area is what? This is 75. 75 minus 12.5. What is that? It's 68.75. Okay. So this area is 68.75 multiplied with 12.5. Thickness is 12.5. 12.5. So that's, you can write it. That's, you can write it. 100. Sorry. So 100 multiply with 12. Multiply with 12.5. That is one area. That is one area. And another area is what? 68.75 multiply with 12.5. Multiply with 12.5. Multiply with 12.5. That is another area. So distance, where it is acting? Where it is acting? Exactly off, na? Exactly off. Because that every portion is acting Fy only. Every portion is acting Fy only. If you consider every portion is Fy, so exactly where it is acting? Exactly where it is acting? Exactly off, na? Exactly off. So what is that value? What is that value? So total is 67. Total is what? 75. 75 by 2 divided by 2. So this is, we want to find out the compressive force. So that is the compressive force. You can take it as, so tensile force also same. So what is MP? 250. This area, this analysis multiply with lever arm distance. What is that lever arm distance? 75 by 2. Exactly 75 by 2. Exactly. Okay. Exactly what is the distance? This is the distance and this is the distance. So this is distance is 75 by 2. This distance is 75 by 2. So this is, if you see, M is sigma into ZP. So no, if you find out the MP, you can find out. They ask for the only shape factor and plastic moment capacity also find out. They also find out it. So if you find out it, you will get it 55.175 kilonewton meter. Just find out ZP. Just find out plastic moment neutral axis. See, plastic sectional modulus. If you find out ZP, you will get it. You will get it. So 2.204 10 power 7 mm per cube. You will get it. So he asked what is the shape factor. So what is shape factor? Shape factor is Zp divided by Z. So what is Z? Z is section modulus for elastic analysis, that is I by Y. So that is I by Y. No? So what is I? Can you find out I? For this section, can you find out I? So parallel axis theorem, perpendicular axis theorem, you can find out it. You can find out, you will get I is 13883464 mm per 4. Y is 75. You already know it. So that is what Z is. Z is 1.81851 into 10 power 4. See 5 mm per cube. So what is shape factor? So this divided by 2.20 divided by 2.201. So divided by 1.851 10 power 5. It is not a 7, it is a 5. So what is that value? That value is 1.19. So that means 20% strength is beyond a yield point. Okay, that is a shape factor, that is a plastic moment capacity, everything. Okay, can you find out? So that's it. So directly I came through the I section. You feel something awkward, not awkward, something sudden jerk. So I will show you in rectangular section. I just missed it. So if it is a rectangular section, see it is. This is a stress. This is Fy, this is Fy. Understood? Both are Fy. So this is, if you see, we already calculated yesterday. M is Fy into Z. So what is that Z? That Z is I by Y. So what is I by Y? PD cube by 12. That is I. Y is D by 2. What is that? Fy is BD square by 6. Yesterday class we proved it. Are understood? Yesterday class we did it. BD square by 6. Same. Compressive force, tensile force multiply with lever arm. You can get it same. Otherwise I by Y also you can get the same. Are understood? Yesterday we did it. Fy into BD square by 6. But if you see, this is a Z. If you see the same section, plastic moment capacity, you see it. That's it, na? Equal area axis is same. Same CG is equal area axis also. This is a neutral axis for elastic analysis and plastic analysis also, because the top area is what? It is a B, it is a D by 2, it is a B, it's a D by 2. Equal area axis also same, because equal area axis means what? The area divides exactly off and off. Same, na? Same. If it is different, I will solve another problem. Okay, today I will solve another problem. See, every section reaches to the Fy. Every section reaches to the Fy. This is Fy. Now you can calculate the plastic moment capacity. This is C, this is T. So MP is same, Fy into Zp. Sir, what is Zp? Plastic section modulus. Sir, how can you calculate? Can you calculate by like this only? Like this means this is equal to C or T multiplied with lever arm. What is C? So Fy stress area is what? PD by 2. Tension force also same. Don't need, because same equal area. So same, this time is reaching to Fy, that time also reaching to Fy. So what is this distance, sir? This distance is, see, this is D by 4, this is D by 4, this is also D by 4. So lever arm is D by 4 plus D by 4, it is D by 2. Okay, so what is now Fy into BD by 2 multiply with d by 2. So see, Fy by d square by 4. Now we can see. Directly I am going to the I section is something wrong because you can't understand directly I section. Now we can see this is m. M is Fy by bd square by 6. That is Fy into z. Okay, that is the elastic section, elastic resistance, yield resistance. For plastic, Fy into bd square by 4 is increasing. Na? This is exactly Fy into zp. Fy into zp. Now you can see the z is this value, zp is this. What is the section shape factor? What is the shape factor? So zp by z, that is bd square by 4 divided by bd square by 6. 6 by 4, it is what? 4 4 z 2, 1.5. That is 1.5. Now you can see in a rectangular section 50% strength is there beyond the yield stress. Beyond the yield stress, you can say up to yield stress, it may be its capacity is, it is 50, it should be equal to 75. 50%, 50% of in 50. Otherwise it is 100, it is 150. You can easily say by the elastic analysis, you can say automatically you can say what is the plastic moment capacity. You can easily say by the plastic moment capacity also by just knowing the elastic capacity. In the elastic capacity, it is 100, it's 1.5 times. 50% extra strength is stored in the system or in the material beyond the yield point. Got the idea? What is the shape factor? Got the idea of the shape factor? So, can you find out the shape factors for different shapes? Can you find out? Different shapes? So, I will show you. Shape factors for different shapes. So, now it is a section is some circular section. If the section is circular section is the circular section. Can you find out? Can you find out the shape factors? So exactly this is the equal axis. Equal axis. What is z? Z is I by y. So what is I? I with respect to the neutral axis. What is I? I is I is section pi r power 4 divided by 64. Okay, I is what? Pi r power 4 by 64 or 32 or 16? 16 I think. Okay, 16. What is an exactly? What is I? What is an I? So I think it's not in 16 also. It is I. It's a polar axis. So I think it's an 8. It's an 8. Okay. So that is the I. Divided by y. Y is what? Y is r by 2. So not r by 2. It's what? It's r. It's r. Y is an r. If you taken as r. So exactly sorry. It is not a pi r power 4 by 8. It's pi r power 4. I. Pi r power 4 by. So sorry. If you take a d, pi d cube by 60, pi d power 4 by 64 will come in d. So that's why I confused dr. If you take a diameter, pi d power 4 by 64 will come. If you take an r, it's pi r power 4 by 4. Okay, that's it. Na? So r d is 2r. If you take an 2 power 4, 16. 16 by 64, 1 by 4. That is I confused. Okay, so taken this, you will get it what? Pi r cube by 4. That is the section modulus. What is ZP? ZP is directly just delete Fy. Just delete Fy. Just take care. This is a compressive force. This is a tensile force. That's it. Na? That is a tension force. That is a compressive force. Multiply with area area multiply with this lever arm. That's it, na? Area multiply with lever arm. That's of area multiply with lever arm. That is a C or T. C is what? That area of the top multiply with. So that is area multiply with Fy. So moment is C multiply with Fy. So Fy, C is area into lever arm. So area multiply with lever arm is ZP. Area multiply with lever arm is ZP. Are understood? So delete it Fy. Again, everything you don't need to calculate Fy. Directly you can find out ZP is half of the portion of area multiply with lever arm. That's enough. That's enough, na? So now you can find out. Now you can find out ZP. Half area is what? Pi pi r square by 2. That is half area. What is this lever arm? What is that lever arm? The lever arm, this is what? This height is what? Its height is 4r by 3 pi. So okay, 2 4r by 3 pi. Lever arm, na? This is also 4r by 3 pi. So that is section modulus. You can find out the section modulus like this for plastic analysis. Plastic section modulus. Okay. So no need to write again m is equal to c into t or something. Half area and multiply with lever arm. So what is that value? That value is pi r cube. 2 can cancel, 4 by 3. Again pi will come. So again pi will come. So again pi will cancel. 4 by 3 r cube only. Okay. 4 by 3 r cube. So what is shape factor? Now shape factor is 4 by 3 r cube divided by pi r cube by 4. R cancel. So what will get? 16 by 3 pi. It is 1.698. So got it? 70%, almost 60% is there. So by this you can say one thing. For rectangular sections we will use only, so not only I can say rectangular section, after the yield point 50% strength is stored. We wasted it. If you take in a circular section, after the yield point 70% strength is there. We didn't utilize that. So much wastage in the circular section. Are you at the point? We will use only elastic analysis. 70% strength stored after the yield point. We won't utilize it. We won't utilize it. That is a waste if you're doing the elastic analysis. Got the idea? Why it is purpose? Purpose. You required purpose. So if you like this, if you see another section is, if you take in some I section. I section has so many dimensions, not so many dimensions. If you take an I section, 2n problem. If you take an I section, symmetrical I section, we did one problem. What is that? 1.19. Mostly it will lies on that only. Mostly shape factor values. Okay. Shape factor values only lies on 1.12 to 1.18 or 19. If you take any dimensions of I section, the shape factor is lies on only. So if you see this, you can conclude like only 10%, 10 to 20% strength after the yield point. So if you do the elastic analysis, it's okay. We don't waste so much energy. It has later only 20% is there. 20% is there. But if you see circular section, 70% strength is there after the yield analysis. That is won't utilize it. Got the idea? So, and also if you see a triangular section is there. Section is triangular. The shape factor is 2.34. Too much. 200%, not a 50%. 230%. Double, triple is there. Almost 2.3%. 3.3 means 200%. If elastic analysis you doing, the moment of resistance is 100. If you do the plastic analysis, it will 234 will come. So you will only design for 100. It has a capacity of 234 at the ultimate. We wasted so much. Na? So that is the idea. If it is a triangular section is 2.34. Take one triangle section and do analysis. Do the value. Otherwise we will do it, but no. If you see a rhombus section, if it is a rhombus section, it reaches to 200 200 is 100 is there. 100% is wasting. If it is 100, it is will come 200. Exactly 100%, double. Same 100% is wasting. Okay, got the idea? Those are the idea. Those are the idea. Okay. Now we can see. I will explain one thing. You have a doubt. In what is a plastic neutral axis? What is a plastic neutral axis and elastic neutral axis? Elastic neutral axis. So this is the equal area axis. Equal area axis. This is the CG axis. Sir, how it is both different? I will show you. For small section, I will show you. If it is a triangle, it is a P. If it is a H, it is a H. So what is the CG here? What is the CG? CG axis is where it is located? Exactly at somewhere. It is a CG. It is a CG, na? So how much height is there? How much height? H by 3. You already know it. That is the CG. That is the elastic neutral axis. Sir, equal neutral axis, equal area axis is plastic neutral axis is what? Where it is? Where it is? Somewhere is there. Somewhere is there. It exactly divides the area into half, 2 parts. Exactly area into 2 parts. Sir, CG is doing the same? No. Just check it is. CG is doing the same? No. No chance. Equal area axis. This is the plastic neutral axis. Plastic neutral axis. How much distance from the top? Can you find out? Can you find out? So I want to find out. So can you find out? So I will try to find out. I will try to find out. So see it is. How can I find out? So H, B, height and width. Height and width. So H by B is a constant. Na? So for H distance it's a B. For 0 it's a base width is 0. Somewhere I think it is a plastic neutral axis. The height is H dash, width is B dash. H by B is constant, na? So for this H, this is a B. For this H, this is a B. So is everything is decreasing same ratio, na? Same ratio. So now I can conclude it. I can conclude. H by B is constant. So somewhere it is a plastic neutral axis is there. It is exactly divides the area into 2 parts. So now I can say H by B is H dash by B. B dash. H by B is equal to the H dash by B dash. Are you got the idea? So get the idea. So now we can see. I said this is the half of the area. Exactly. So both areas are equal. I say I am taking both areas are equal. So see what is the area of the top of H dash B dash is equal to the below area. So that is why now there is a plastic neutral axis exactly divides the area into 2 parts. So top area this, bottom area, no need to write bottom area. So exactly top area is half of the total area. Half of the total area. Can write it? Half of the total area is what? Half HB. That's it, na? That's it. You can write it like this. So now this of cancel. This of H dash B dash is HB by 2. So by this, you can write B dash is, how can write? H by B, sorry, reverse it. B dash you can write B H dash by H. You can write, na? You can write it. So now I will write it. H dash is B H dash by H, HB by 2. HB by 2. H dash square is equal to B cancel H square by 2. So what is H dash? H by root 2. H by root 2. That's it. So now you can find this H dash is H by root 2. Previously the CG is this from bottom H by 3. Equal area axis is somewhere higher, H by root 2. So that is the shifting of the neutral axis from elastic analysis to the plastic analysis. Plastic neutral axis exactly divides the area into two parts. Why it is divided? We explained previously. But the CG axis is center of gravity line. That is the momenting. Based on the moment, you will get center of gravity, not area. Got the idea? That is shifting. So, okay. So you can easily find out. I will show once again another also. If it is I section, I will show in I section. I will show I section. It is 100, it's a 20. It's again, it's a 20. Simple problem. It's a 100. If it is 100, it is a thickness of 20. If it is I section, take it as I section. So now you can see what is exactly the CG axis. CG axis is somewhere here. How can you find out? By the moment. Write down. So somewhere by the moment, from this position you can write from by this line. How can you find out the CG? By this line, 100 into 20 area, and this distance is 10. And also this area, second area, again this is 100 into 20. This exactly it's 50. Exactly 50, na? By this line will come as a 50 plus 20, it's a 70, divided by total area. Total area is this. You get CG. So what is that CG? That CG is 40. So that means the CG is 40. So 120, this is 80. This is 80. So that is the CG axis. Are understood? That is the CG axis. Sir, what is the CG axis means? Neutral axis for elastic analysis. For plastic, neutral axis is neutral axis plastic, or equal area axis. Equal area axis. Exactly the line divides the both areas. Divides the area into half. Where it is? You can easily say here, this is 100, this is 20, this is 100, this is 20. Exactly this is the line. Got the idea? Top area is 100 into 20, bottom area is 100 into 20. By looking. So this is a plastic neutral axis. This is the elastic neutral axis. The difference between this is 20. Got the idea? So that's it. That is, I want to show you today what is the shape factor, load factor, factor of safety, how it is the plastic axis is different. Okay, so I will give one assignment, not assignment. I will show you one thing. I will show you one thing. The last someone mostly they showing this. Okay, if it is a rectangular section, take this. So d by 2, so b. Okay, for elastic analysis, this is Fy, this is Fy. For plastic analysis, this is. For elastoplastic analysis. So what is that? Some part under plastic, some part under plastic, some part under plastic, some part under elastic region. This is elastoplastic region material. If you use like this, we use total, it's a plastic analysis. So we already know it. What is know it? For elastic analysis, what is the moment carrying capacity? Fy into Z. That Z is PD square by 6. We already decided. It's compression force, this tensile force. For moment carrying capacity in total fully plastic, we already decided, we already calculated. What is that? Fy into Zp. What is that Zp? BD square by 4. We calculated. If elastoplastic region is there, so I will decide that is E. That is the E. What is the moment carrying capacity of this section? What is the moment carrying capacity of the MEP? Can you find out? Just find out the same thing. You have to find out this compressive force and later this compressive force. Both are clubbed it. So same thing, this is the tensile force. This tensile force, you can club it. Can you find out? So I will find out it. So see. So for this region, this is the compressive force, this is the tensile force. For again the same region, this is the compressive force, this is the tensile force. No need to add this C, this T, and you have to find out the CG of those region. No need at all. Individually, you can join it. For this moment, you can both it. That's the same also. For this region, C, T. For this C, this T, multiply with lever arm, you can easily find out. I will show you. And explain. See, just last topic today. So now you can see, for these two regions are there. One region is this. One region is this. One region is this. We will find out the moment capacity, moment resistance through this region, top region and next region. Individually and add it. Okay, got the point. So first I will show you. First I will find out the top region. This is a E, na? That is a E. That is a E. So what is that? What is that compressive force? What is that compressive force? What is that compressive force here? Fy. Area is what? Width is B and depth is E. And what is the centroidal lever arm distance? This. And again for this tensile force, this is tensile force. We will take care like this. This is the C, this is the T. We will find out only that portion. The lever arm is, this is the lever arm. We will take care that portion and later remaining portion. You can add it. No need to add total compression force in this portion and find out the CG of that portion. No need at all. Are understood? So you will find out like this also. So that's it. And what is the lever arm? So this distance is, you can easily say it is E by 2. This distance is also E by 2. So total distance is D minus of E by 2. So otherwise D by 2 minus E by 2. This is also D by 2 minus E by 2. So you will write, so 2 into D by 2 you minus C, 2 minus C divided by 2 to cancel. D minus C. This distance is D minus C. Okay, got the idea? So that is for first part. Second part this is now compressive force, this is now tension force. We have to find out what is the tensile force, compressive force, anything you can take it is same, Fy, but it is off. So no need at all to find out again. So directly if you see this, if it is this region, like this region, it's by BD square by 6. Directly you can find out the Z. See this region. This is the region. That's why I will draw. This is the region. We have to find out now. So exactly it's look like this. You can directly say BD square by 6. But it is not a D. What is that value? D minus 2E. Because this is a E left. This is a E left. D minus C. You can find out by compressive force multiply with the lever arm also. You will get the same thing. Yesterday we did it. So okay. So for this region, Fyy, it's a area is what? So BD square by 6. B is B. D is not D. D minus 2E. D minus 2E whole square by 6. So now you can add both. That is the moment carrying capacity of the elastoplastic material. Fy Be D minus C plus Fy 1 by 6 B D minus 2E whole square. You can find out like this. You can find out like this. If anything, someone asks, 50% of the portion reaches to the plastic. If 50% of the material reaches to the plastic region, 50% is in elastic region, what is the moment carrying capacity of the rectangular section? Someone asks. If 100% elastic region, we know it. 100% plastic, we know it. If only 50% portion reaches to the plastic zone, 50% is in elastic zone, how can you find out? What is the moment carrying capacity? You will find out like this. E is now D by 4. 50% na 50% reaches. 50% reaches. So like this, I will develop like this. E is some alpha D. E is in alpha D. 20% of D, 30% of D, 50% of D. Like this. If it is E is alpha by D, you can rewrite. You can rewrite it. MEP is, you can rewrite in terms of alpha B, alpha D minus C 1 by 6 B alpha D to C. Why write? So D minus E is alpha D. D minus 2 alpha D whole square. If you differentiate it, if you write it, you will get like 1 by 6, add it, Fy by BD square, 1 plus 2 alpha square will come. Add it like this. Okay, that's it. So I will write it. Now I will write it for 1 by 6. I will write it as a 1 by 4 and 2 by 3. So why it is, sir? I will show you. 1 by 4, 2 by 3, Fy BD square, 1 plus 2 alpha square. If I write it, so now you can observe it. MP is what? Fy BD square by 4 na? Fy BD square by 4, that is MP. So that's why Fy BD square by 4. So now it is 2 by third 1 plus 2 alpha square MP. That is MEP. Now we can observe. Now we can observe it. If alpha is 0, MEP is exactly equal to the how much percentage? Alpha is 0, put it 2 by 3 of MP. 2 by 3 means 0.667 of MP. Otherwise, for the rectangular section, what is a ZP? What is MP by what is M? What is MP by M? It's 1.5. 1.5, no? What is M by MP? It is 0.06. That is 4 by 6, 6 by 4. That is the same. If it is alpha is 0, that means fully elastic. Alpha is 0 means fully elastic. Fully elastic, that is a MEP is 0.67 of MP. If it is alpha is 10%, 10% means just put 10% means 0.1. Alpha is 0.1. So MEP is 0.786 MP. So like this you can calculate 0.2. It is a 0.88 MP. If alpha is 50%, 50% means see, E is a 0.5 D. E is 0.5 D means what? E is 0.5 D means total. This is D by 2, this is D by 2. Total section is in plastic analysis. If E is 0.5 D means what? It's total E. So if E is 50, E is 5, this is equal to MP. This is equal to MP. Like this you can easily find out. These are the data. For this rectangular section, this is the data. For I section, some data. For circular section, you can get the data. So how much the strength is beyond the yield point? How much strength beyond the yield point? What is the shape factor? If how much percentage we allow in the plastic region, we get how much we get more strength. How much we get more strength. We will use, whether we will use or not, you can decide by the designer. That's this type of one graph. Okay. So that's it. Today's class is that's it. So now you can idea about what is the plastic neutral axis, what is the elastic neutral axis, what is the shape factor, what is the factor of safety, what is the load factor. Okay. So how can you find out the plastic moment capacity resistance or elastic moment capacity resistance? Got the idea? So